the search button. I said if you're using Windows, it's quite easy, but if you're using MacBook, I think on MacBook, it's you just open it. It's still relatively the same, but Linux is mostly Bash, so it's totally. But they are all the same. They all do the same thing. So if you have installed Python and Jupyter Notebook, um, you can easily just type in Jupyter Notebook, for example. And once you click this, it's going to open on the browser. Now, for me, I like to use Jupyter Notebook because it helped me to really interact with my code, and it's kind of make me to follow what my code is doing, and it makes sense for me because I don't have to run the whole script, write the whole script, and then debugging. So sometimes it could be very, very tedious, especially for some of us who computer science was in our background. So it's kind of makes sense if I have to be watching the code at every time. I don't know if you get my point. So that's why I usually move. So when I finish doing the script on Jupyter Notebook, when I want to deploy it in form of an app or something, I find a way to write the Python script and then I deploy. But the reason, once I make sure the Jupyter Notebook setting is running, and then I could deploy. And also you could have, if you don't have Python and Jupyter Notebook, you can also use the resources online. Yeah, you can use the Google Colab if you don't have the Jupyter Notebook on your system right now. You can use the Google Colab. Google Colab, it's very, very free. It's available to anyone. You could use it. All what you need to do again is just type on your browser Google Colab, and then it's come out. So Google Colab does the same thing. And again, the good part of Google Colab right now is that it's been linked with generative AI like Google Gemini. So it could even make suggestions. For example, let me see if we could open a new notebook in Drive. Okay, yeah, let's see. Yeah, great. So great. So you could see this, it comes with generate with AI. So it's been linked with AI. So if you don't have Jupyter Notebook, I think Google Colab could also do the same thing. So feel free to use any of them that you want. So either you go the other way. But again, for me, it depends. The advantage of using Google Colab is that it will be saved to your drive online. So even if you have like a crash or something on your system, you can always know that the scripts are safe, and you can always come back to retrieve them. But if it's on your system, sometimes it's not safe. But like me, what I do is I usually backed it up so that once I do those things, I could still be able to retrieve them, put them in the cloud facility. So any of the formats you decide to use is totally fine. So, but from from my end, we'll be using this. So I've sent you the script. So if you download the script, you can be able to. So if you are going to be using Google Colab, all what you need to do is to be copy. You can copy them, and then you go back to the script here. You paste them and you run them. But before you run, you would need to install some of those things because there are some packages that Google Colab may not have. For example, sorry. Okay. Let me see if I could show you what I mean. Although I know Google Colab, yeah, it's likely going to have all these packages here, but there are some packages it will not have. So you will have to install them, or you run into error. So it depends on which one you want. So you can copy them from the script. Good. So it ran fine. So you can be copying them from here and then you take them there. So depend on what you want. So let's look at what we have today. So we talk about hyperparameter tuning, and I told you about what hyperparameter tuning means. We need to get optimal values that best fit the problem. And then we said you cannot do this hyperparameter tuning except you optimize it, because keep trying going back and forth could be very, very tedious. So we talk about the grid search. It helps you to optimize this hyperparameter. And then we also talk about the cross validation, as two approaches. So and we also gave the reason why we're talking about why we have to bring in hyperparameter and also cross validation because of overfitting, underfitting, and then training time and parameters would increase. And I told you guys, the more you increase those things, the more computational resource you will have. And then another thing is you're always looking for a way to improve the performance of your model. So today let's look at example of regression problem from our previous class. We're looking at regression, but it's going to be a different problem we're looking at today. Still housing problem, but the other one was boosting housing problem in boosting still United States. The second one we are looking is California housing problem. So first of all, you need to load the required library package from Python. So these packages, for those people that don't know about them, they are algorithms that have been developed by experts in the community. So these packages help you to put your data set in the right format, help you to prepare them, help you to remove missing values, and so on and so forth, and then also help you to fit the problem. So you don't need to, for example, write the package from beginning. So all what you need to do is to make sure you get your packages in the ready format, and then you could just run them. So package like NumPy, for example, handles a lot of things that has to do with array, matrix, and all that. Pandas will also does some of these things. So handles some of those things. Also some little mathematics problem like the mean, median, mode, and all that. Then the Scikit-learn or the Scikit-learn is the usually ones that have all the traditional machine learning algorithms like logistic regression, random forest, decision tree, and so on and so forth. But things like XGBoost, for example, it's not really in Scikit-learn because it was a latter approach that came up. So it has its own package. And we'll talk about that. But right now, I just wanted to focus on the simpler models. So for you to do that, you need to install these packages but if you are using things like Anaconda, you're likely going to have most of these packages followed. But if you're using if you're just installing Python and all, you will not have them. So what you need to do again, you can watch the previous videos to see how you could install them. But generally, you install packages using pep install. And then you could also install the package on the Jupyter Notebook. All what you need to do is to open a new cell. Then you could, if you have to install on the Jupyter Notebook, you need a sort of a hyphen or something, and then pep install, and then the package name. So let's say you want to install pandas, you now run it. So once you run this, it will install it, and then all what you need to do is just come back to your kernel, refresh, and you run. However, that's not what we are going to do today, but this is how to install package. So you could say how to install package. So again, most of the time we use the hash to express comment that we want to make. And then I usually like to suppress the warning because it's kind of going to make my scripts dirty. So make sure you when you're writing scripts, take note of some of these things so someone can read your scripts and understand what you're doing. So next we need to load this data. So this data set, for example, is already in the package. You can see from Scikit-learn dataset. So the dataset is already here, but you can have your own dataset. So if you have your own dataset, you have to read it through a path that you can call the dataset. So, but what we're using today, these are examples that the dataset is already in the package. So, but again, if you want to see how to read it, I think the previous example I shared how you could do that in the previous script. So you could go and look at it also to see how you can be able to do that. So next thing you do is to load the data set. But again, you don't just work in isolation. Try to visualize what you're working with. So df.datahead helps you to see a preview of your data. So again, run that to take a look at how the data set looks like. So this gives you like an overview of the content in your data set. And then the next thing is to run to check if you're going to have missing values. So the f dot is null, in bracket of some missing, help to for each of the variables. So again, in this data set, the columns are the variables that you are going to be working with. And then we have this target. So depend again on the name that they call these things. So why you're doing this is to find a way to identify missing values. Because if you have a missing value, the problem is you can have some algorithms that do not work with missing values. So they will raise errors and you have to go back and fix them. So it's better you have a preview of your data set to see if there is going to be missing values. So another thing again that I like doing a lot is check a brief descriptive statistics on my data set. How does these things look like? So that way you can be able to know what the mean looks like, the median looks like, the standard deviation and all that. So again, this helps you a lot, especially when you're trying to do missing values. You can be able to have an overview from there and then you know how to be able to fix it. So again, you run this. So once you run it, you take a look and see what you have. So at least from here, you could see that the maximum value in this data set here is 15, while the minimum is around 0.5. So things like that, you could have an overview of it. So the next thing we'll do is to perform EDA or exploratory data analysis. So the reason again is that this really help you to familiarize yourself with your data. You can't work with like this saying goes, you can't give what you don't have. You can't explain what you don't understand. So in order for you to be able to solve the problem of your data, you need to make visuals, create visuals, interact with them, visualize them, see how these things are distributed, see what sort of relationship is happening in the data set. So that way you can be able to tell the story better. Because AI, data science, or machine learning, these are just a way of us trying to understand the real world. And people or persons tends to understand the real world more in graphics compared to audio format. So it's good you make visuals in order for you to understand what you are doing. So the package for making visuals or graphs in Python is the matplotlib and also Seaborn. Now there are other packages you could also use, and we could see them as we continue in this journey. So next thing we do is to run this to see what's happening. So this is a histogram between we're looking at the distribution of the housing price. So we're looking at the price on the x-axis and also the frequency on the y-axis. So clearly you could see that a lot of them are concentrated on 0 to around 3, they're about 2, but there is a slight decrease, and then there is this guys that stood out there on the 5 side. So in Nigeria, we could say these are the guys that lives in the Banana Island or the VI or some of these Twitch places and all that. So you have the slight words, then that's where the large majority of people are, and then there is this place where you have the junk words. So again, the essence of doing this is to just have a view of the distribution. How skewed is it? Is it something that you needed to? Because sometimes when these values are not really okay, it will still be giving you some issues. So you need to perform some sort of transformation like log transform in your data set. So that's why it's very good for you to see these things. So you don't just put in the data into the model, because the model is more like a garbage in, garbage out. So if you don't ensure that what you're putting out there is makes sense. Your model will be looking so nice, but again, it's missing some of the patterns that you could have picked up if you were being careful. So it's good to make these visuals. So another visuals we want to make is a sort of a scattered plot to see what happens. Now, scattered plot is very good in explaining relationship as well. So most of the time you usually use it to understand what sort of relationship. Is it a kind of a positive sort of relationship, or is it a negative sort of relationship? Now, when you looked at the scattered plot, you could see quite, yeah, it's more of a positive relationship, but again, there is still this guys on this five that are quite different from the other ones. So again, we could do another thing, which is to me, it's very, very important. And if one of the take-home message of this class, I'll say the correlation plot is very, very nice. Why did I say so? Because most of the time, these variables that we collect sometimes tends to compete with themselves. And when they compete with themselves, they slow down the target variable. Because it's just like, imagine you having players playing in the field, and then some of the players, when they are supposed to score goal, no, like everyone wants to score goal. Nobody wants to pass to his neighbor or to the other person. So that will make them, at the end of the day, they will not achieve the aim because they are competing among themselves and their opponents may defeat them. So that also happens when we are developing prediction models. Sometimes the model competes among themselves. So the way for us to be able to know which, variables. So the way for us to know which variables are competing among themselves is for us to visualize them via correlation. So correlation, again, is nothing but relationship that could be positive or negative. So if the relationship tends towards one, we say it is highly or strongly correlated. But if it's going towards -1, we say it is strongly negatively correlated. So it's either is strongly positively correlated or negatively correlated, or it's just average. So, however, in the case of machine learning, there is what we call the variance inflation factor, VIF. So what we do is that the VIF will help us to identify the futures. And don't worry, I think the next class we'll focus more about future selection. We'll talk about some of those things again in detail. But most of the time, the VIM will help us to be able to screen these features that are competing with each other. But again, in the case of correlation, most of the time you could set cutoff. There are not really been any uniform agreed cutoff. I have seen a situation where people remove the variables when it is up to 80 or 70. So it depends again on your own personal choice. But when we talk about feature selection, you could see we will talk about how you could automate some of these things, and you don't have to do them yourself. It will just automatically remove them for you. Maybe when you use some sort of personalized regression models. But again, we'll talk about them as we progress. So here, one of the notable issues I noticed on collinearity on this is the fact that average rooms and average bedrooms seems to be competing among themselves. You can see there is a strong positive correlation, which is around 0.85, that is going on between them. So if this class is focusing on talking about future selection, you will likely see us talking about how we can remove one of this feature, because obviously the two of them will be slowing down the on the target variable. So we don't need the two of them. So what you may need to do is to prioritize them. Do you need to focus on average bedrooms and remove the average rooms or not? So you could remove them. And again, if you looked at this, there seems to be terms that are the same, because the average rooms and the average bedroom seems to be the same, although they may not, because these days the average room could even be sort of a study room or something. And all that. So again, it depends on the terminology and what you're looking out for, but they clearly seems to be having high correlation among themselves. So if you are in performing things that has to do with maybe pattern recognition, of course you could leave them. But if you are developing prediction model, you should know that your aim is to find the best way to capture the target variable. So because of that, you don't need to be keeping variables that will be competing among themselves. So again, the aim of your study and the kind of things you're doing will determine how you do away with some of these things. But if you notice these kind of things, you need to prioritize which of them you should pick. For example, I'm going to tell you a study that I'm doing currently. I get these biomarkers on chronic kidney disease from Nurture, that being about 3,000 patients. And then they give me these biomarkers. There are about 25 of them, or even more. What I do is that, first of all, I developed an association study where I did lots of statistical stuff, where we try to establish what sort of relationship is happening between the urine biomarkers and also the blood biomarkers. So then in the blood biomarkers and the urine biomarkers, when I visualize them using the correlation plot, I tend to see this sort of correlation happening in some of them. So when I'm developing prediction model for them, I begin to drop some of those variables. So, but what again I do is I use other approaches, not necessarily the correlation, to select the best futures for that I'll put into the prediction model. But it's kind of telling me that they don't need everything. And then when for example, the latest one that I did that we're currently writing the paper is trying to see if there are differences in the biomarkers in the prediction of outcome variable like kidney failure and even mortality between male and female. So I developed prediction model for the first 2 years and also the next 4 years. So I discovered that for female, for example, I had only 3 biomarkers that were determining the heightening the risks in them. The biomarkers like NT, PN, BP, and also troponin and so on and so forth. I wouldn't want to use this complex medical terms actually. So then in males, I discovered we had like just 2 of the biomarkers. So I recommend to them that, okay, probably you guys can validate these 2 biomarkers in your labs. So they are happy because they don't have to focus on all the 25, because what they want to do is that they will repeat this measurement again for the patient, but they want to focus on the biomarkers that are highly sensitive in predicting the clinical outcomes. So they don't have to waste the resources to repeat the experiment for the whole 25 that they collected at the baseline. So when you are looking at resource prioritization, you have to put some of these things into consideration. So you don't have to be doing everything at the same time. So again, so you could see between longitude and latitude, there is a strong negative correlation among them. So take note of some of those things. So, but outside them, I don't really see any correlation as such, but you could use them. So again, like we said, the interpretation, if it's 1+1, it suggests strong positive correlation, and if it's -1, it suggests strong negative correlation. So in order for us to go into the modeling phase, the next thing we need to do is to prepare the data set. Now, preparing the data set meaning you are going to tell the model this is independent or future set or matrix, and this is the target variable that you want to predict. So normally what we do, we assign X for the independent variable. And this is kind of, from the mathematical sense, most of the time we talk about summation of X equal to X1, X2, X3, and so on. So it's still the same. We're still keeping some of this how do I say, representations even in the algorithm. So the same way we usually use the X, but you could use anything you like, but these are more popular. So the X and then the Y. So, but what you need to do is to ensure you drop the target variable. So that's what you see. So normally, what is the target variable? You drop it. So here the target is called the target variable. Here it's still target. So you just drop it and then you assign that target variable to Y. Then the next thing, remember from our slide here, we talk about the training and testing. So the next thing you need to do is to split your data into training and testing. So it splits the data. Training and testing. So this is what you're doing. So when you notice here, we use 0.2, it means we are telling the algorithm that we are going to take 80% as training and we are keeping 20% as testing. Then this is just the random seed. So you see random state 42. So you could change this random seed the way you like. You can say it's 1, it's 0, it depends on what you want. But normally, I think 42 is quite a good one. So the random again is just like you're telling each time as you're doing this splitting, you reshuffle it and take it out in that pattern. So that's what it does. So it just splits it. So, but before you do this data processing, if you have missing values, remember to take care of them before you come to but because we don't have in this case, that's why we're just going straight to this point. So again, you run this. So the next thing is to train the model. Like I said, start from the simple one. So we're starting with logistic regression model, which is the simple one. So again, you load the logistic regression model. Then the next thing you do is to fit the model and then you make prediction. So remember, prediction you are making only on the testing set, not on the training set. So, but you have to fit on the training set. So you first define the model. So this is just the model. And again, this is a simple one. So we are not putting any estimates here. We're not putting any parameters, just the model itself, and then we see. Now, what we are doing in this phase, we are not performing hyperparameter search. We just want to see, does this performance look good? How is it going to look? Just want to have an overview of the whole thing before you talk of, shifting the goalpost. So this logistic regression is just acting for us as the baseline. So remember, you have made the prediction. So the next thing now is for you to check the predictions score. So again, you could see that you have the mean absolute error to be around 0.53. So kind of small. Then you have this mean square error around 0.56, which is kind of better. And like I said, the mean square errors sometimes generalize well more than the absolute error. So again, we would look at the root mean square, which is quite great, around 74. But then we also looked at the R square, which is the percentage that was explained, of the variation that was explained. When you looked at it, we have around 58%. So it means we have 48% that was not accounted for by our model. So you cannot really say this is a good model because you could see clearly that there is quite some guys here that you cannot. And this 42% thereabout, they could hold a lot of good information that you cannot just throw them away and say you are okay with the model. So you need to go further to check and get to know what's happening. So next we need to do is to visualize the model to see how it was able to capture this variability. So when you run this, again, we're using the matplotlib, and now this is the y test and this is the prediction, which is y pred. Then the actual value is on the x variable and the y is the predicted value. So again, this is what we are doing. So you could clearly see from our straight line that we do leave out some good information from although the model did perform nice, but again, we did leave out some good chunk of information here, and we did leave out some other information here. So we need to investigate further using more complex model. So we're not going to train random forest to see what can we have. Can the random forest do better than what the logistic regression have? Most cases will always have random forest outperforming the linear models. But again, you cannot tell because not every problem that you see the complex model doing better than the simple model. So again, you define the random forest. And then if you notice also the computational time for the random forest it didn't fit quickly like the regression did. You could see it's kind of taking time. So that's what happens. The higher you increase the complexity of the model, the more it takes time. Because, and again, random forest, these are decision tree models. So what they are going to do, they will sort of kind of go into to understand each instance in the model. So it has finished running. It means we have trained the model, and now we have made prediction. So the next thing we need to do is to look out for the prediction. How are they looking like? So again, we are looking at the mean absolute error. So you could see that the errors did decrease. Huh? We could imagine the errors here were from 53, 0.53, 0.56. But now that you use a complex model, can you see a drastic decrease? Can you see it reduces to 0.32? Because that's what we want. We want to be reducing the error as much as we can. We don't want this error to be big. We want them to be very small. And these errors, they are errors on the testing side. Remember? So we talk about the biasness and the variance. So this is good. 0.25 is around 0.26. Sorry, it's way smaller than when we have 0.56. Then the root mean square is also around 0.51, which is 0.51 compared to linear. The baseline model was around 0.7 something. You can see here we have around 0.75, which is much more compared to what we have here. Then the root mean square again of the percentage of the explained variability, it improved very well, 0.81, which is great. It means we are only leaving out 19% thereabout. It makes a lot of sense. So if you see, it means that this problem, random forest actually tends to understand it better than the logistic regression. So another thing we do now is to visualize the model. Again, you could see that really random forest did understand the problem. And like I said, most of the time we're looking at the patterns that it captures. So really we could see that there is quite an improvement compared to, although we didn't have some perfect model, but we're looking for something that actually understands the pattern in the data set, which is what we could see. So another thing again is that we want to perform grid search, because somebody will now say, I can push the boundary. I'm not okay with 81%. I still want to see if I could get 90, if I could get 100, if possible, and all that. But 81 is a good score. It means it's only 19 times of 19% of the time that you're going to be getting it wrong. But still, you could, check and see what's happening. So, like we said, for you to perform the tuning, you need to define them. And we usually use this parameter grid to define them. So now you talk about the estimator, which is you also talk about the model depth. So this would sort of the parameters you want to tweak. So you could increase them. That's why I put a hash here that you could use 50, 100, 200. Again, like I said, depend on your computational resource. But I would advise, in fact, I have seen where people started from 2, 3 and all that. So depend on what you want. You could start from small, you could, so you could change the estimators to see, but usually start small and then you could increase them subsequently. So you could also see the maximum depth. Now, the maximum depth is how you want the tree. Do you want the tree to be shallow or you want to increase them? Because when we talk about the maximum depth, this is what we mean here. I think in the previous class, I did talk about them. Great. Yes. So if you can see this slide, yeah, great. Now, this is what we mean by the maximum depth here. So if you keep increasing the tree, you will see it continue to go down. So do you want it to be a very deep tree or you want it to be shallow? So depend on what you want. So what we do is we talk about pruning, but we'll talk about that in other time. So you could prune it or you could make it small. So this from the root node to the leaves is what we talk or consider as the maximum depth. So that's what this one is talking about here. So you could see the maximum depth. Then the minimum sample split. Again, this one now talk about the splitting. So if you can again see this particular figure here, it also talk about this splitting here. Great. So you could see the way this splitting goes is what is talking about. So how do you want to be splitting them? What is going to be the minimum split? So usually, of course, you could start with 2 because you can't say 1. So if you start with 2, 5, 10, so again, you could play around with each of them. And then, so what we are doing here, we are not trying to say, we want to perform. So you can also embed in the grid set, you can put the cross validation. So you could see CV equal to 5. So we put the cross validation inside the regression model. So again, it depends on what you want. Some people don't put it, they will just search and then they put it later on in the best model. But in this case, I think I put it in both the grid search and the best model. So, but any of the scenario you want, you could put it in the grid search. You could put it also after you have performed the grid search. So depend on what you want. So, but I put it in both just to make you understand that you could play around with these things. So, you notice that it's going to take time compared to the normal fitting. So I don't know, I didn't actually time how long this take, but probably like 5 minutes or something is going to take before it's finished running. So this is why, again, I want you to understand when I was talking about the computational resource that always think about these things, because do you have the time, to do it? Because yes, your model will improve somehow, but sometimes you need to put these things into consideration. But these days, suppose I'm using a GPU, it wouldn't have taken up to 1 minute, because if you are putting it on a cloud or any platforms that has big resources, it's much more faster. But if you're going to be using your CPU or machine learning tasks, always think about these things. The bigger the parameters, the higher the computational side, because these are MP problems. So again, it's going to be exploring large chunk of your RAMs in order for them to do the calculation. Somebody may be wondering, like, what we are trying to say. I don't know if you remember your Pascal triangle. I think that was the first thing we did in remedials when we started remedials. They tell us about Pascal triangle where you start with I think 1, then 2, 1, 2, 1, then 1, 3, 3, 2, 1, like that. But you could see in the Pascal triangle, the more you increase the powers, the more the triangle will continue to, go down. So that's the same thing when we're talking about this computational research. Once you increase these parameters, you're increasing the computational time. So these things will have to take time to put them together. So I think it's my fault. I could have used a very small parameters, but I wanted you to understand what I meant by talking about this computational research. So, but maybe next time I would have used a very shallow one that would not have to waste our time. Anyway, I can still pause it if you want, and then I use a very simple one. But if you don't want it, we can allow it to run. So I don't know, depend on what you guys want. Do you think we should allow it to run, or we should stop it and move on?
Yeah. I think since we have started it, let's just watch it how it goes.
Okay,
To me.
but yeah, it will soon finish running actually. Yeah. I did time it when I was preparing the script, but I think it was around 3, 4, 5 minutes there about it stayed before it finished running. But I did remember actually. So what I noticed was that if you have access to higher computational resource, don't be afraid to play around with this thing, because really, the more you explore them, the more better. Because out there, people will question you to know what you have done. Nobody wants to settle for a shallow thing. So a lot of people will ask you, did you do this? Did you try this? Did you try this? Again, so if you explore those things, the better for you. But sometimes you have to also check speed and those things. For example, for a PhD researcher or master's student, you are raising with time. Maybe you need to produce your paper. You need to finish your research within the first 6 months or 2 years of your research, or 3 years. So you can't continue to be going over these things. So you have to find a way to strike a balance between speed and also doing a very quality thing. So most of the time, you should have access. Don't train these things on your PC if you are going to be trying lots of these things, because you will run for. I've seen the ones that have run for weeks, and it was even on a GPU. So I could imagine if it was on my local computer, it would have taken maybe 3 months or more. So then things like deep neural networks, when we start looking at it, you will notice most of the time I'll be switching to the Google Colab. I'll be using this Google Colab when we're looking at deep learning, because this Google Colab provides me with the resources. I think it gives us access to GPU or something. So you're not really using you can see it's kind of connected to cloud. So it makes sense if you want to try out some of those things. But normally, deep neural networks, you won't be able to run them on your system. You just have to use additional resources. So my advice is, when you have this complex model, find additional resources to help you speed up the process. Then yeah, so this is quite crazy. I think it was my mistake. I could have used very, very simple model, but okay, next time it's fine. But when you are trying it at your end, if you have access to all this computational resource, feel free to try any of the complex model you want. Anyway, so
Yeah, sorry. Is
okay,
there
so in the meantime, do anybody have questions that we could tackle before it's run? And I'm sure it will run very soon. Do anybody have question?
yes, I think I do.
Okay.
Is there a trade-off between computational overhead and performance of model?
Yes, there is. Because the more you see, one of the things you guys need to understand is that the more it computes, the more it's going over the data in a very diligent way. So you will likely see a lot of improvement in the model. So there is a trade-off between, but again, the problem is that you don't know the outcome when you're doing these trainings. So you cannot conclude. Sometimes you will put in all the hard work, and then you see the model will come out to perform poorly, not fitting what you want. So you have to make sure you keep going until you get. So it's kind of tricky, So most of the time, okay, it has finished running. So most of the time, there is no one way to achieve these things. It's kind of, you go back and forth, you check, you tweak. Like I told you guys about cooking. So you put the spice. Oh, it's too salty. You put water. So you keep, going back and forth until you get the best thing that you're looking for. Okay, so it has run, and now we could see that the depthness, it doesn't consider any of the depth. It means it was using the default one from the model, and then it was using the minimum of 2 split. However, the estimator it went for was 50. So it was actually using lots of big estimator, but it was the tree was not that it was not a deep tree. It was quite a shallow one. So I think the next thing we need to do is again, I performed a sort of a cross validation. Again, the cross-validation we are doing in this case was on the best parameters, which was this one. So the grid search helped us to identify the best parameter, and then we put in that best parameter in the model. So now, instead of us to be using every other thing, we now say, okay, now we have seen the best thing. So we now pick that best parameter. And suppose you want to deploy your model, which we'll be talking about those ones also in our next study. We will begin to see us talking about some of this best parameter thing, because you're likely going to be saving the best parameter, not just the anyhow parameters of your model. So again, you could see the mean of the cross validation, the absolute mean, it actually went down. You could see it did reduce. The error was very tiny. So this tells you that it did happen. You know, the more you do that. So next thing we will do, we will make predictions, still using the best parameters. But before we make prediction, we will fit the model again, because this cross validation, grid search helped us to identify the best model. So by doing so, the next thing we could do, we can now refit the model on the training, and then we make prediction. So instead of us to settle with the default model, we tweak it somehow, we got the best one, and then we refit the model again. So by the time you run this fitting, I don't think this will take time again. So by the time you run this, we expect to get values that are better than what we gotten before now. So I think it reduced. I think we have around 0.33 and around 0.25. That's like 0.26 for the mean square. So let's see what we have on the absolute. Okay, so we have around 0.33 till 0.25, and then the R score was around 0.8, which is around 80%. So it didn't really improve the model as anticipated compared to what we have before we perform the check. So that's why it's good for you to first of all do the default model and then perform the grid search. Then you can be able to see, did it really improve my model or it did not. So at least this gives you a hint that the grid search did not. So maybe what you are going to do next is to go back again and tweak them and see. Then you come back and compare. But even if you have exhausted some of this tweaking, because maybe you may not likely have any improved one compared to the default, then you go with the default. You don't have to perform the hyperparameter in this case. So, but again, in the classification case, it will not be the same. You will discover the hyperparameter do improve the model. So here in this case, it didn't improve. But when we are looking at classification, you'll see that it did improve. Sorry, I noticed it's already 2 hours. So I don't know if we have to pause the class for today. But do you want us to finish the classification? Okay, I don't know. Depending on what you guys want. But it's already our 2 hours. So I don't know if you guys want us to finish, or we can continue next week. Looked at the classification and then we go into yeah. So Monday said it's quite
my whole system
interesting.
will soon shut down, and there's no
Okay.
light.
Oh, sorry about. So this is again some of the resources problem we were talking about just now. So I think we can. This is a good place to stop for today.